Hello and welcome to this clip on condensation polymerization. We'll start by reviewing some of the addition polymerization of alkenes that you did in your first year and introduce the idea of a copolymer where you get more than one monomer involved. We'll then look at the idea in chemistry of condensation, where basically two molecules react and combine and a small molecule is released as a byproduct. Then we apply this idea to polyesters and polyamides to introduce the idea of condensation polymerization, and then we finally have a look at deducing the repeating unit of a previously unseen polymer as an example of application style thinking. This will be done via an examination question. So before going any further, it's important to make sure you're already comfortable with addition polymerization from your first year of A-level chemistry, and also that you've covered the chemistry of esterification and the formation of esters, because this chemistry will be applied and it'll be assumed that you're comfortable with the general idea to start with. And we're also going to assume that you're familiar with the chemistry of amines, and particularly their basic nature, i.e. the fact they behave as bases. So we already know that addition polymerization occurs in alkenes, because as you remember there's no other product apart from the polymer. So the alkene that you start with is called the monomer, and the repeating unit is basically the alkene with single bonds in the middle and the trailing bonds coming off the side within square brackets. So the repeating unit is the basic unit that the polymer is made of, but many repeating units make up the polymer chain. Sometimes what happens is you get more than one monomer and they can alternate in the polymer chain. So a repeating unit would obviously be AB, repeated n times. And remembering that n is a very large number. So an example might be propene and chloroethene polymerizing together to make a copolymer. So like we mentioned in the introductory slide, condensation polymerization happens when two monomers react. The important thing is that a small molecule is eliminated each time the monomers react. So it won't be an addition reaction, it's not 100% atom economy. So one common example of condensation polymerization could be between dicarboxylic acids and diols. Let's take a moment to have a look at why these are dicarboxylic acids. You can see clearly that you've got two carboxylic acid groups, and in the diol you've got two alcohol groups at either end, one at either end that is. So during esterification what happens is the OH group on the carboxylic acid and the proton from the alcohol combine together to make water. So that becomes an eliminated small molecule, water. So it's important to remember the ratio of repeating unit to water is n to 2n plus 1. So one of the most common sources of confusion when doing polyesters like this is how to deal with the trailing bonds. So at the carboxylic acid end, you remove the OH completely, and at the alcohol end you just remove a hydrogen. It's important to remember this. So hydroxycarboxylic acid is a carboxylic acid that has a hydroxyl group somewhere else in the molecule, in addition to the carboxylic acid group it already possesses. So an example of this would be lactic acid. So let's have a look at how we construct the repeating unit this time. So taking the alcohol end, we just remove the hydrogen. If we now take the carboxylic acid end, the OH is removed this time. Okay, let's have a look at another example. But before we go any further, it's worth pointing out that both the examples looked at so far are involving esterification So these polymers are called polyesters. So just looking at the formation of the linkage between them first of all, before we start looking at what they might look like as polymers. The reason they're called polyamides is you get something called the amide linkage. And your amide linkage is this, the C double bond O with an N attached to the carbon and an H attached to that nitrogen. It's also known as the peptide linkage. The peptide bond is something that's referred to quite a lot in biochemistry. So if you're taking biology as well as chemistry, you may have heard of the peptide linkage already. So this is the model of the peptide molecule. Or to be more precise, it contains the peptide link, so it's called a peptide. So from your work on amines, you'll have come across amino acids. So amino acids contain the H2N group and also a COOH group. Now if you have these on adjoining molecules, they can react with each other by removing a water molecule. So what that does is gives us the amide link we talked about before, plus our water molecule that comes off. If we do this repeatedly, we'll get a polyamide like the one we've got at the bottom of the screen. And also we get our requisite number of water molecules produced as well. So here's another example of how several units might actually join together, so how several monomers might come together, releasing a small molecule each time to produce a polymer chain. So this would obviously be a polyester, this particular example. So here we have two ways of forming polyamides, and in the top version I've shown where the amide linkage actually is, in blue. So basically what you've got is either a dicarboxylic acid plus a diamine, or at the bottom you can have two amino acids reacting with each other. So if we were to take amino acids and to react with each other, what you'd get happening basically is that water would be eliminated by the reaction of OH and NH2. So because the carboxyl group is acidic and the amine group is basic, they'll have an acid-base reaction with each other. So you'll end up with a polypeptide. So you can see clearly the peptide link that's produced by the removal of water each time, and you end up with a polypeptide. So here's a bit of an exercise for you. See if you can grab a piece of scrap paper and work out what would happen if these were to be combined with each other. So pause the video and come back when you think you've got an answer. So this is the kind of thing you're aiming for, a repeating unit of some kind. If you look really closely, you'll actually see there's another place down here where further polymerization could take place. So as you can see, the more complicated your amino acids and the more COOH or NH2 groups they have coming off the side, the more possibilities there are for polymerization in different directions. So just as a quick reminder, here's a closer look at the formation of terylene. You can clearly see it's a polyester. You can see how the H2O molecule is removed, and you can see how the repeating unit is put together using the techniques and the features we talked about a little bit earlier. So just as a reminder, as you can see on the alcohol end, from the ethane 1,2 diol, you remove the hydrogen but leave the oxygen. And on the carboxylic acid end, as we talked about in this case for benzene 1,4-dicarboxylic acid, you remove the OH entirely. So terylene would be the trade name, basically, for the polyester that's formed at the bottom. Trade name is used by the company, chemical company that patents and discovers, in other words, the the method, the chemical method and reaction for making a polymer. If that polymer turns out to be extremely useful and therefore can be sold and profit can be made from it, the patent process is there for the company to legally make sure that they are the only people who can make and sell it, and it can't be copied by anybody else. So the patenting process is not something really you have to worry about in your chemistry A level, but it just explains why there's certain trade names that are used, like nylon or Terylene or Kevlar, for a description of different polymers. Each of those particular trade names will have a story behind it. Someone will have discovered it, and that someone will be working for a chemical company, and therefore the chemical company have the rights to that particular polymer's manufacturing technique. So here's some common uses of the polymers we've just talked about. We can include polyesters in clothing, obviously. And just in case you're not convinced, there's a picture of one of my dodgy shirts. I'm not actually joking, this is one of my shirts. So moving swiftly on, we can now have a look at what happens when polymers, or condensation polymers, actually react. This is another application, not an application, but another feature of them, because you have polar bonds present in the linkages, in the polyester, in the ester linkages and in the amide linkages. That means these bonds are susceptible to attack by water, which makes these polyesters and polyamides biodegradable. This is an important environmental consideration, which we'll look at next. And just so you know, the TM next to each of the names stands for a trademark, and basically this is in reference to the patent many chemical companies hold on the name of the polymer their chemists discovered. So Dacron, Terylene, Kevlar and nylon are not the chemical names, they're trade names. There will be actual chemical names that each of those polymers have. So it's important to be able to deduce what the products will be if you have a base hydrolysis or an acid hydrolysis. So hydrolysis is essentially using water to break up the ester linkage. So I'm looking at polyesters here, obviously. So the example that we've got shows a polyester made from a diol, which is this part here, and a dicarboxylic acid, which is this part here. Obviously you can also get polyesters when you have a COOH group and an OH group on the same molecule. We looked at lactic acid earlier. Let's have a look at what lactic acid might do if it's hydrolyzed with an alkali and if it's hydrolyzed with a base. So if we were to take this and apply it to something like polylactic acid, what would happen is the OH minus of the sodium hydroxide would be the species that would be hydrolyzing the polylactic acid. And if you warm polylactic acid with sodium hydroxide, aqueous, you get sodium lactate. And simultaneously you'd have the regeneration of the alcohol group from where it was before. So the salt part of it, sodium salt over here, will be formed at this point. So if you look at the acid hydrolysis, this time the H2O is the species doing the hydrolysis, and this time you get the lactic acid back, not a sodium salt. Where the sodium ends up is producing the salt of the added acid, so the added acid is HCl. So these two reactions are definitely ones that you'll want to go and practice on several different examples before it starts to sort of solidify itself in your mind, because it's fairly complex, or it appears to be fairly complex the first time you try it. So it's worth going away and doing a bit of repetitive practice on some different examples to make sure that you become familiar with how to apply this. Because what will happen in exam questions is they'll give you new examples of polyesters you won't have seen before, and very much ask you to apply the knowledge that you're learning to those new examples. and it can be quite long questions as well, with quite a lot of marks allocated to them, so it's worth going away and doing the practice on this. And just remembered I've been a bit naughty, I've forgotten to put my N on the polylactic acid. So always remember to put N next to your square brackets. So sorry about that if it caused any confusion. So if we look at acid hydrolysis of the amide link this time, you can clearly see that water plays a role as well as acid. So what happens is you get a positively charged quaternary ammonium salt. So let's say the acid was HCl. What would happen is that you'd have Cl- bonding ionically at the point that the positively charged nitrogen atom as part of the quaternary ammonium salt would form. So you'd get a quaternary ammonium chloride forming. So when you're looking at alkaline hydrolysis, the key thing to remember is you get a carboxylate salt of the alkali, and you also get the amine group regenerated. What I've done is I've put the amide linkage, or the peptide linkage, whatever you want to call it, in blue, so you can see the destination of the two parts of it, so you can see how it's split. So this time it's the OH- is the hydrolyzing species. So let's have a quick look at the environmental considerations of the different types of polymers that we've looked at so far. One more consideration to have about polymers is their biodegradability in the environment. So with addition polymers having no polar bonds, they don't tend to break down very easily, and they can actually survive in the environment for hundreds of years. Whereas condensation polymers have polar bonds, which makes them susceptible to hydrolysis in alkaline or acidic soil. And as such, condensation polymers, or items made from condensation polymers, tend to break down more quickly in the environment, which is an important consideration in today's world, where we're trying to make sure that we don't leave things in the environment that are going to stay in the environment for a long time. It's also quite important in the marine environment, where small pieces of addition polymers, small particles of addition polymers, find their way into virtually every single marine organism in some way or another. And because they don't break down, they're actually quite a serious problem in the oceans across the world. Condensation polymers, on the other hand, break down easily in the presence of water, because water will always have a slight acidic or alkaline character to it, and this will help the hydrolysis process more quickly. So at A level you have two types of polymer. You have addition polymers and you have condensation polymers. So looking at the monomers first, for an addition polymer, the monomer will always be an alkene. For condensation polymers, the monomer could be either one substance with two functional groups, or two different monomers, each with two different functional groups. So an addition polymer will always be formed via an addition reaction, whereas a condensation polymer will always eliminate a small molecule, and it will be happening via condensation type reactions. And finally, addition polymers are non-biodegradable because they don't have any polar bonds, so they don't hydrolyze or break down in the environment. But because of the types of linkages, amide and ester linkages in condensation polymers, they can be easily hydrolyzed, as we've looked at already. So in acidic soils or alkaline soils that we find naturally, they tend to biodegrade over time, so they break down in the environment. So let's work our way through an exam question. It gives you an example of two polymers. One is mandelic acid and one is ethyl methacrylate. Now in each case it tells you what the actual compound is, and in the case of ethyl methacrylate it also tells you it's an addition polymer. So the first thing to do is to explain what's meant by the term condensation polymerisation, and you'll see that they've actually put an extra piece of information here, which means you should actually be including appropriate technical terms, ideally spelled correctly. So you need to have both those points, and your technical term is obviously a monomer, and you've also got to say that a small molecule such as water is eliminated. In the next one, they ask you for 2 repeat units, so it's very important you actually follow this instruction. So if we draw out mandelic acid, it's quite clear that there are 2 places where the reaction will take place, but it's on the same molecule, so what you've got to do is visualize what's going to happen when that molecule polymerizes. So you'll see that I've drawn the monomer twice because they want 2 repeat units, not just 1 repeat unit. So there's definitely something to watch out for in polymer style questions. How many repeat units do they want? So we've got our ester linkage for 1 mark, and we've got the remainder of the structure for the other. So let's pull the page down a little bit. So we've already been told that ethyl methacrylate is an addition polymer. So remember, that must mean that you've got a C-C double bond somewhere in the original monomer, beg your pardon. Another thing to spot is the ethyl methacrylate molecule, or monomer, already has an ester linkage. So you don't have to draw a new ester linkage that's formed. An ester linkage is already there. So remembering as well that we were asked to do 2 repeat units, if I just quickly show you where the repeat units come in. So the double bond has been changed into single bonds by addition polymerization. Right the way along the chain, like so. So it's often worth trying to draw out the monomer first so you can visualize what it's going to do in this type of question. It's a very, very common question style where they give you something new you won't have come across in your textbook or your notes and ask you to apply what you will have learned from your textbook or your notes to that new compound and try and suss out what it's going to do. So the next question says, when ethyl methacrylate is heated under reflux with aqueous dilute acid, a hydrolysis reaction takes place, forming compound C in ethanol. So it actually tells you there's a hydrolysis, and it also tells you that ethanol is one of the products. So the thing to do would be maybe to sketch out your structure for ethyl methacrylate again, so you can visualize what it's likely to do here. And because we're talking about hydrolysis, obviously this time it's the ester linkage that's affected, not the carbon-carbon double bond. So because the ethanol will clearly be coming from this part of the molecule, it's this part of the molecule that will form compound C. So that's why I've put in the answer box that particular structure. So moving the page down a little bit, it says, when compound C is heated with steam in the presence of an acid catalyst, an addition reaction takes place forming 2 organic products, D and E. So in other words, you're hydrating the carbon-carbon double bond. So this is coming straight out of your first year alkenes chemistry. You get a product like that, and just to confirm where the water came from, there it is. So obviously you get a mixture of products, and that would be compound E as well. So it says compounds D and E are structural isomers with the molecular formula C4H8O3. So if I move the page down a little bit, we can do the structural isomer of that compound. And again, we can highlight for illustrative purposes where the water was actually added. So let's move on to the next page. It says mandelic acid has antibacterial properties and is used in some skin creams. Cosmetic chemists use mandelic acid to prepare 2 different esters that might be suitable for new skin creams, and the 2 structures are shown below, ester 1 and ester 2. So let's just remind ourselves what mandelic acid looks like. So although this isn't technically the answer, it's just a drawing of mandelic acid. So all I've done here is I've highlighted what this particular compound in the question looks like. So we want ester 1. So let's look carefully at mandelic acid. Mandelic acid has a benzene ring, so does ester 1. Mandelic acid has an OH group, so does ester 1. Mandelic acid has a COOH group, and ester 1 has the C double bond O of a COOH group. So what we want is to know where that came from, or in other words, how that turns into this part of ester 1. So what you need to put is the structure that's in the box. All I've done is I've drawn it out as an equation so you can see how the mandelic acid will react with that structure to make ester 1. So let's now move down the page again. It now asks you about ester 2. So just have a little look at ester 2 again. And I'll just draw it in for you. And I've also drawn in the mandelic acid at the beginning. So, let's have a think about this one. First thing to do is to identify the mandelic acid in both the left and the right hand side. Okay, so what we've got to do is think of a molecule that could create or could provide the part that hasn't been highlighted in blue. So that would give us this particular molecule. I think you'd probably call it 2-methyl propanoic acid. You could also put down an acid anhydride. There'd be nothing wrong with doing that as well, because that would be a perfectly legitimate reagent to produce ester 2. So let's now move on to it says ester 1 is less soluble in water than mandelic acid. So if we think about what they're trying to drive at here, we're talking about physical properties as opposed to chemistry. So they want the difference in water solubility of mandelic acid and ester 1 actually to be explained. And it's a good idea here, if it says to use a label diagram, it's a good opportunity rather to put down again the structure of mandelic acid and the structure of ester 1, just to remind ourselves. Except what I've done this time is I've put in the displayed formulae of the OH groups and also the dipoles. Because if we're talking about solubility, we'll be talking about hydrogen bonding. So if we now put in some water molecules, and we also label the hydrogen bonding, and then we explain that mandelic acid has one OH group and one carboxylic acid group. So therefore mandelic acid can form more hydrogen bonds with water than ester 1 can. So moving the page down, the final part says before any skin cream can be sold to the public, it must be tested to make sure it's safe to use. And they want you to give a reason, and that's to check for side effects or toxicity. So look at the mark scheme now. We got the monomers, and we talked about the small molecule produced in addition. We got this correct structure with the ester linkage, and we got this structure as well, showing the single bonds that are produced when you get addition polymerization. We got our compound C and the two isomers of D and E, and we also got the correct alcohol. Interestingly, that would be wrong connectivity. What I mean is the hydrogen would not connect to the rest of the molecule, it would be the oxygen. we got the two possible options. You didn't have to put both of them in, I just put both so you could understand that either of them would do the job. We got the idea that the hydrogen bonds form with water. We got the idea that mandelic acid forms more hydrogen bonds, and we said why, because it's got a COOH group and an OH separately. And then finally, we're looking for adverse side effects or toxicity. So hopefully you found this a fairly useful clip. It's a bit longer perhaps than some, but it's because there's quite a lot to cover in polymers, so I wanted to make sure I was doing it thoroughly. If you've got any queries, jot them down and bring them in to your teacher, or possibly see one of us in a subject extension. In the meantime, thanks for your time, and thanks for your effort, and we'll see you soon.